Greetings to the students. So, in this video, we are going to learn about residues at a point. Residues of an analytic function at a point. Okay. So, first let us see the definition of residue at a point. Okay. Let A be an isolated singularity for f of z. Okay. So, first, let us learn the definition of isolated singularity. Okay, so first, before know about isolated singularity, let us see the definition of singularity first. Okay, so singular points is nothing but at which point analytic fails, that point is called as a singular point. Okay, wherever the analytic fails, whichever points the analytic fails, that point is called as a singular point. Okay, so a point A is said to be a singular point if f of z is not analytic at that point. Okay. Okay, so a point A is said to be a singular point if the function f of z is not analytic at that point. Okay, this is the definition of singular point. Okay, next, isolated singular point. Okay, so isolated singular point means, suppose if we have two singular points. Okay, we have two singular points, 1 and 2. Say 1 and 2. The point 1 is said to be isolated singular point if in that the neighborhood of that singular point, the other singular point too should not come. Okay, which means, okay, yeah. So, okay, so let us consider 1 and 2 are isolated, sorry, are singular points. Okay, they are singular points. If 1 is said to be an isolated singular point if by making 1 a center, we can find so many neighborhoods. By making 1 a center, we can make so many neighborhoods. Okay. If there exists a neighborhood, okay, if there exists a neighborhood, say this one, okay, I'm choosing this neighborhood as there exists. Okay. There exists a neighborhood of 1 does not contain the point 2. That is, in this neighborhood, the point shouldn't come. If it is true means, if it has happened means, we can say that the point 1 is an isolated singular points. That means that neighborhood of 1 should not contain the other singular points. Okay. For example, yeah. Okay, suppose this is our real axis. Okay, this is our real axis, and this point is 0, this is 1, this is 2. Okay, so 1 and 2 are singular points. Okay, 1 and 2 are singular points. If 1 is said to be isolated singular points, there exists a neighborhood. Okay, there exists a neighborhood for 1 by centering for center as 1, we can make so many neighborhoods. Okay, we can make so many neighborhoods. This is a neighborhood, and this is also a neighborhood. Okay, if it is said to be an isolated singular points, there exists one neighborhood. Okay, there exists one neighborhood. I'm choosing that neighborhood as this. Okay, this. Okay, this is a neighborhood for the point 1. Okay, so this is a neighborhood. In this neighborhood, the point 2 didn't come. Okay, if I choose the neighborhood for 1 as this means the point will come. The point 2 will come. But if we choose the neighborhood as this or this, the point 2 cannot come. If there exists some neighborhood, if there exists a neighborhood which does not contain the point 2, then the point 1 is said to be an isolated singular point. Similarly, the point 2 is said to be a isolated singular point if there exists a neighborhood for 2 which does not contain the point 1. That can happen. We can choose that kind of neighborhood which does not contain the other singular points. Okay. So this is the definition of, sorry. This is the definition of a singular point. Okay. Sorry, isolated singular point. So given that, let A be an isolated singular point. Then residue of f of z at that point. Residue of f of z at the point A is defined to be the coefficient of 1 by z minus a in the Lorentz series expansion of f of z about the point A and is denoted by residue of f of z at A. What is the meaning? Okay. So we have A. Okay. So we have A as isolated singular points. Okay. Singular point. Then the residue of f of z, this is notation, residue of f of z at the point A is equal to coefficient of 1 by z minus a in the Lorentz series expansion. Okay. What is Lorentz series expansion? Actually, Lorentz series and Taylor series, they are very powerful tools because they express the analytic function into a power series. Okay, they express an analytic function into a power series. The Taylor's theorem is valid in the region mod z sum less than r. Okay, or in the entire complex plane. But the Lorentz series is valid in the annual region. Annual region means this kind of region, some R1 less than mod Z less than R2. Okay. In other words, for your convenience, 1 less than mod Z less than 2. This is called annual region. In this region, the Lorentz expansion is valid. Okay. So this means what? Okay. Wait, I'll show you. So this is our real axis, x-axis, and this is our y-axis. Okay. So mod z greater than 1 means what? As we know that if mod z equal to 1 means a circle with the center 0 and radius 1. So mod z greater than 1 means what? It contain, okay, this is 1. Okay, this is minus 1 and this is 2 and this is minus 2. Okay, so mod is greater than means what? So this is the circle with the center 0 and radius 1. If mod is greater than 1 means it contains all points outside the circle mod is equal to 1. Okay, so this is the region mod is greater than 1. What is mod is less than 2? This is the region with the circle with center 0 and radius 2. It contains only the interior points. Since it has less than 2, it contains only the interior points. So this is our mod is less than 2. Only the interior points. Okay. Annular region. Okay. What is the meaning of 1 less than mod? That is it must be lies between. Is it satisfies mod is it greater than 1 and satisfied mod is it less than 2? What will be the points? These are the points. Okay. These are the points. So Okay, this is mod z equal to 1. Okay, the circular region. This is nothing but the points which lies in between these two circles. Okay, so this is one. Okay, these points satisfies the condition mod is greater than 1 and mod is less than 2. Okay, so in this region the Lorentz series is valid. Okay, yeah, so Lorentz series is, let me write the Lorentz series. Okay, so Lorentz series is, before that I will erase these things. Okay, so Lorentz series expansion is the analytic function f of z can be written as, this is equal, written as summation bn by z minus z naught the whole power n plus summation a n into z minus z naught the whole power n. Okay, so this is the Lorentz series expansion. In this Lorentz series, coefficient of 1 by z minus a. So here instead of z naught, I am writing a here and a here. Okay, what is coefficient of 1 by z minus a? Of course, b. When n equal to 1, it will becomes b1 by. Okay, when we expand this, what will happen? Previously, so many terms are there. b uh, 2 by, okay, here n varies from 1 to infinity. Okay, here n varies from 1 to infinity, but here n varies from 0 to infinity. Okay, so b2 by z minus a the whole square plus b1 by z minus a the whole power 1 plus, so the second next term is a naught plus a1 into z minus a plus a2 into z minus a the whole square and so on. So here the residue of the function f of z at the point a is coefficient of 1 by z minus a. So what is coefficient of 1 by z minus a? b1. So this is the residue of f of z at the point a. So suppose if the function is if the function is given means you have to expand that function and find the value of the coefficient of 1 by z minus a is the residue of that point. Okay, residue of the function at the point a. So before find the residue, the point should be an isolated singular point. Okay, for singular points only we are finding the residue. If it is analytic at all points means then what is the need of finding the what is the need of finding Cauchy's integral? I mean, need of finding the what to say? If it is analytic at all points, then there is no need to apply Cauchy's integral formula and Cauchy's residue theorem. Okay, we will see the residue theorem later. If it is analytic phase means, then at that point we are finding that value. Okay, at that point we are finding the value f of z naught and the integral value. Okay, so if you are going to apply the Cauchy's theorem or Cauchy's integral formula or residue formula, anything, the point we are applying it for Cauchy's theorem. It is not for singular points. Cauchy's integral formula and Cauchy's residue theorem is only for the points in by the analytic phase. Okay, so to find the residue at the point should be an isolated singular point. Okay. So this is the first definition. A point A is said to be an, the residue of the point, the residue of the function f of z at the point A is defined to be the coefficient of 1 by z minus a in the Lorentz series expansion. Okay, so next definition, residue of f of z at the point A is nothing but 1 by 2 pi I integral over c f of z dz. How it is came? Yeah, I'll show you. Okay. Uh, but, So by Lorentz series expansion, f of z equal to summation of bn by z minus a the whole power n plus summation an into z minus a the whole power n. Here n varies from 1 to infinity and here n varies from 0 to infinity. Okay. So here now we are finding the value of integral over c f of z dz. Okay. So by Lorentz series, we have f of z can be written as this. So when we take the integral, when we take the integral over c, this is equal to integral over c plus integral over c. Okay. Integral over the integral of summation is equal to summation of integral. So summation of integral over c bn by z minus a the whole power n dz plus this term. Okay. So when we expand this, when n equal to 1, this will become b1 by z minus a the z minus a into dz. When n equal to 2, this will becomes integral over c b2 by z minus a the whole square into dz and so on. Okay. So by okay. Okay, this is equal to this value. Since b1 is constant, we will take the b1 outside of the integral. So which is equal to b1 into integral over c 1 by z minus a into dz. Okay. So by the definition of residue at the point, coefficient of 1 by z minus a into dz. Okay. Here we are going to apply Cauchy's integral formula because the point A is a singular point, which means analytic fails, and it lies inside the given curve. So we are using by using Cauchy's integral formula. I'm only focusing on this one because in the Cauchy's residue definition, coefficient of 1 by z minus a only we need to consider. So the remaining we don't need to consider. So by Cauchy's integral formula, this is equal to b1 into 2 pi I into what f of z, isn't it? Since f of z equal to 1, the point f of sorry, this is f of a. Okay, since f of z equal to 1, f of a is also equal to 1. So therefore, this is equal to b1 into 2 pi I. Okay, by taking 2 pi into left hand side, we get, by taking 2 pi I into left hand side, we get 1 by 2 pi I integral over c f of z dz is equal to what? b1. b1 is what? By the definition of residue, coefficient of, okay, b1 is nothing but residue of f of z at the point a, since it is the coefficient of 1 by z minus a. So therefore, 1 by residue of f of z at the point a is nothing but 1 by 2 pi I integral over c f of z dz. They are connecting Cauchy's integral formula into residue. Okay. So I hope the definition is clear to you. If they are asked to find the residue at the point, at some point, at the singular point, what you have to do is you have to expand that function, given function, and find the coefficient of 1 by z minus a in that function, or else you can use the second formula. Residue of f of z at z equal to a is equal to 1 by 2 pi I integral over c f of z dz. If you find this value, then is equal to residue of the function at that point. Okay, so I hope the definition is clear to you all. Okay, we will see the examples regarding residue at the point in the upcoming videos. Okay, so thank you, dear students. Thank you.